Good morning, my name is Rui Matos and I'm here to present the work called The Influence of Driving Imperfections on the Water Pressure Resistance of HZM-AZ Walls. Basically, the organization of this presentation is like the following, starting by an introduction of the topic in discussion about installation of combined walls, numerical modeling, ultimate loading conditions, effect of driving imperfections to the water pressure resistance, discussion about the tool for simplified analytical assessment, and conclusions. Basically, these HZM-AZ walls are steel retaining structures widely used on ports as quay walls, and basically they are a combination of the use of steel sheet piles with special I-beam sections called the HZM beams. These beams, called also king piles, are normally considered as the main bending resistance element. These external connectors, RZD and RZU, they are also used to connect both the sheet piles and the HZM beams, as represented here in this picture on top. And the infill sheet piles, they are designed according to the Eurocode 3 Part 5 to ensure that they are able to transmit the internal forces. And when used in deep excavations, logs or dry docks, these HZM walls, they might be subjected to high hydraulic pressure or water pressure. And in the current brochure of ArcelorMittal catalog, in the product brochure, it's presented the water pressure resistance of nominal HZM walls. These results were evaluated in cooperation with the University of Stuttgart. In terms of installation, this installation is basically divided in three big steps, the so-called pilgrim step method, which basically in the first step the king piles are driven with the help of a driving template to make sure that they are installed in place. Then the template is removed and the king piles are driven until their final position, and finally the sheet piles are installed. The installation of these elements, obviously, it should be as accurate as possible. However, some misalignments, they can occur sometimes, and basically the main objective of this study is to understand what's the impact of these misalignments, also called driving imperfections, on the effect, or their effect on the water pressure resistance of the system. In terms of numerical modeling, and to evaluate this impact of the driving imperfections, a nonlinear model was developed using the software Abacus, and those models were calibrated with the experimental data extracted from tests conducted in the University of Stuttgart. In these tests, HZM 1080A king piles were used, along with the sheet piles AZ 25800 and RZ16 connectors. These models, these 2D models, they were modeled in 2D with CPS 4R elements according to the library of Abacus. These are basically plane stress elements, even though in this specific case the plane strain maybe would reflect better the behavior in comparison with the tests. However, the plane stress elements, they were considered as a safe-sided approach. Anyway, the real behavior of an HZM wall would fall very likely somewhere in between plane stress and plane strain results. The mesh of this model was considered to have at least 3 elements over the thickness to make sure that the bending effects were obtained or estimated properly. However, a more refined mesh was used in areas where higher stress variation is expected, like the radius of the beams, the connectors, the interlocks, and so on. Different multilinear materials were as well used according to the values extracted from the coupon tests done in the experimental campaign. The boundary conditions, obviously, they were done in a way to mimic the conditions of the tests, and it was used this RP1 to RP3, reference point 1 to reference point 3, to act as points of load introduction. The model was solved with control displacement, and the dynamic implicit solver was used for better convergence. Of course, when we are using a dynamic solver, it's important to compare the kinetic energy with internal energy, and it was observed that it was quite low, meaning that it's expected that no influence of inertia effects are in stake here in the results obtained. A good agreement was obtained when comparing the numerical results and the experimental results. We see that the maximum load is very similar for both, and the trend of the curves is also quite similar. Also, the final deformed shape was very similar in both cases when comparing the numerical and the experimental results. In terms of ultimate loading conditions, two main methods can be used to estimate the ultimate load. One is the stability approach, the second one would be the strain approach. In this specific case, the strain approach was used, which basically consists on the definition of a maximum admissible strain to be reached. In this specific case, it was considered that the maximum admissible strain would be 60% of the fracture strain, as recommended by the Swedish code BSK99 as necking strain. Since we are talking about an S430, we are talking about 11.4% of maximum allowable strain. The necking strain was considered in this case due to the lack of information about the real behavior in transversal direction, so we consider that it would be a safe-sided approach. In terms of the effect of driving imperfection to the water pressure resistance, it was considered horizontal and vertical displacements and rotations, both in the right and the left interlocks, as we can see here in these images on the right. And also it was observed that the vertical displacement could be analytically represented with great accuracy by a set of horizontal stretching and simultaneous rotations at the two interlocks. So this vertical displacement was disregarded and assumed to be included in the other imperfections. So, following this procedure, it was possible to obtain values for the water pressure resistances and for the systems with driving imperfections, and of course to obtain ratios for resistances between nominal and imperfect solutions. The failure mode for each case was also registered, and the snap-through was also considered as a possible failure mode as well. Main trends identified in this study. So the first one was that the most common failure scenario was the development of a plastic hinge on the RZD connector, and the second was the development of a plastic hinge in the AZ interlock but on the side of the RZU connector. Those were the most relevant failure modes. Also, the compression of the system imposed a beneficial effect in terms of water pressure resistances for normal direction. In reverse direction, there was almost no influence. And the stretching of the system led to a reduction of the water pressure in normal direction. However, in reverse direction, the same conclusion was taken. When the system is analyzed in reverse direction, the driving imperfections, in fact, they act as a membrane-like behavior of the HZM wall, which in fact it may result on a high increase of water pressure resistance. And the higher it is the applied rotation on the interlocks, the higher it is the reduction of the water pressure resistance. Now speaking a bit about the tool that was developed. The tool was developed, in fact, taking into account the ratios between the systems with and without driving imperfections. We call them the RI. And it was observed that the linear multiplication of the function was proved to be a good approach when merging the individual ratios for the different imperfections, meaning that if we get individual failure modes, we can combine them together in a combined failure mode only by linear multiplication of the factors. This tool was validated for the range of imperfections analyzed, plus minus 200 millimeters of stretching and plus minus 15 degrees, and the accepted accuracy of the tool was set to be as plus minus 10%. To achieve this accuracy, some extra factors, some weighing factors needed to be used. We call them WI, and they are different for normal and reverse direction. These factors, they allow us to get an accuracy of about 95% in this tool. And basically, the tool will allow the user to obtain the reduction factor for the water pressure resistance in comparison with the case of the nominal system. So in here we have once again the driving imperfections considered, and in here we have the expression. So basically, as we see, we have a combination, a linear combination of the factors, the R factors and the W factors, which will give us the reduction factor for a given driving imperfection. And in here we have the final expression, which is basically the multiplication of this factor by the nominal value. In terms of conclusions, we see that the HZM wall is one of the main solutions for retaining maritime solutions and for deep excavations. It's possible and it's likely that some driving imperfections may occur during driving, and a model was developed and calibrated to estimate the water pressure resistance reduction under driving imperfections. And a tool was estimated based on the results obtained, and it was validated in a range of plus minus 200 millimeters of stretching and plus minus 15 degrees of rotation, with a global accuracy of 95%. In case of extreme imperfections out of this range, it's proposed that a specific analysis would be required for a given case, and our technical department would give a specific detailed analysis for each specific case. Thanks a lot for your attention, and all the best.